Hello, I would like to welcome everyone to the first annual AMP conference. I'm really excited that all of you could be here with us. I would especially like to thank Jonathan and Drew for organizing this. It's my hope that this will be the first of many AMP conferences. A conference like this will help bring together those doing great pupillometry work and those interested in pupillometry all in one place. I really think that this is a great venue to share ideas and knowledge as it relates to pupillometry. Most of the talks you have heard or will hear over the next 2 days will be about the back end of the pupil pipeline. That is, what are some of the issues when analyzing pupil data? For example, the talk right after mine will deal with how you apply pupillometry to babies. And you'll also hear talks about different ways to analyze pupil data and the different methods that are available. My talk's going to be a little different in that it's going to focus on the front end. Specifically, today I want to talk about a package I created called Gazar. And Gazar is a package to pre-process your pupil data. It's my hope that you will give Gazar a try if you have not done so already. The field of cognitive pupillometry has been around for over half of a century now. And the field is growing at a steady rate. As proof of this, I recently did a literature research through PubMed using the keyword pupillometry that spanned from 1940 to 2019, and those results are depicted here. I've placed a vertical line on 1960, which can be argued to be the start of cognitive pupillometry, with the study by Hess. And then shortly after that, we have studies from Hess and Polt and Kahneman. And we see from 1960 to 2019, we've seen kind of the number of pupillometry articles or papers grow. I did include in a previous graph 2020, but I decided to exclude that from this particular figure because 2020 is not over yet. But again, kind of just to reiterate, the field of cognitive pupillometry is growing and it's becoming more and more popular. More and more studies are using pupillometry, which is good for us. And this increase in the number of studies employing pupillometry is arguably the result of advances in eye tracking technology that make it really easy to record pupillometry. We can now record pupil size with any modern eye tracker. Any modern eye tracker will be able to output a pupil size metric for us to use. And in addition, we can do so cheaply. Now, there are eye trackers that are very expensive, but recently there are some eye trackers have come out that are pretty cheap and affordable. So for a few $1,000s, you can record pupil size. You can do pupillometry studies for a few $1,000s. Gone are the days that you have to record pupillometry manually, like what's depicted in this picture right here. If you've read some of the early pupillometry work, you know what they had to do to record or measure the pupil size. So they use some, special contraption to project the pupil size to a wall, and then they had someone measure it, presumably an RA, with a millimeter ruler. So you had an RA taking out a ruler and measuring pictures of pupil sizes as it relates to some type of a stimulus or stimuli that are being presented. And I don't know about you, but I'm very, very happy that we have modern eye trackers that can do this for us with relative ease. And boy, do I feel bad for the individuals that had to do that. Despite the growing use of pupillometry, there is no standard practices in terms of pre-processing pupil data. Just pick up any pupillometry paper and turn to the methods section and you will find tremendous heterogeneity. You can open up a paper and go to the methods section and you'll see that researchers did XYZ. And then you can look at another paper and you can see that a researcher did A, B, and C. And what makes this even worse is that many researchers write in-house code that is never shared because it entails the secret sauce that leads to really compelling results. And if it is shared, it's not well documented. I've gone to many repositories that stores code, and the code is not documented well. Sometimes there's no README file. It's just kind of code in a vacuum. Furthermore, some of these programs are not freely available. And I'm looking at you, MATLAB. I believe this provides an impasse to scientific progress. It goes against the principles and practices of open science. And what I want to do right now is I want to talk a little bit about GAZAR, what it is, and also why I created it. In a nutshell, GAZAR is a pre-processing package I created with the help of Matt Wynn, Tristan Marr, and Dan Merman. It's for analyzing gaze data coming from the visual world paradigm and pupillometry studies. For the purpose of this talk, I will only be talking about the pupillometry parts. To provide a little background, as a grad student, I struggled to find good tutorials on analyzing pupil data. I couldn't even find anything that was accessible to me as a starting out grad student and interested in pupillometry. When I started as a postdoc, Dan Merman was already working on the gaze portion of GAZAR, and him and I met, and I threw out the idea that we should combine his gaze functions with my pupillometry functions that I wrote over the years to help me analyze my pupil data because I couldn't find anything accessible or any good pipelines out there. And out of this came GAZAR. So why did I create GAZAR? Well, one of the reasons, as I kind of alluded to already, is that there just wasn't many pipelines available. And as I was working on GAZAR, I saw this slowly change. I saw more and more packages coming out to process pupil data. So what I have listed here are two great packages that I can't endorse enough. That even if you don't like GAZAR, you don't want to use GAZAR, there's other packages out there, and I implore you to check those other packages out. And I list two of those packages right here. One is Pupillometry R by Sam Forbes, and the other is Pupillometry by Jason Tasaka Kurhara. I definitely encourage you to go visit their GitHub pages and check those packages out. Another reason I created GAZAR was that I wanted a package that was an end-to-end pipeline. I wanted to be able to take raw data from an eye tracker, pre-process that data, analyze it, and visualize it all within the same program. When jumping from program to program, that introduces many errors and really makes transparency hard. Currently with GAZAR, you can, do this end-to-end processing with SRILink, with EDF files, and coming soon, I will have a function that will allow you to read in Tobii data. The ultimate goal is to be able to do this with all eye trackers. I wanted a package to be as simple as possible to use. I wanted a package that simplifies the pre-processing steps. And over the past few years, there's been some great papers that have come out that have helped guide, this goal. And those papers are by Jamie Riley, Matt Wynn, and Sebastian Matteau. And these papers have really, helped me and have guided me in, implementing some of these things in GAZAR. And finally, I created GAZAR because most of the pupillometry functions, or the psychophysics, has been housed in MATLAB. And this leaves our users out, like myself, and those who can't afford MATLAB. They can't afford the license. And if I can get on my soapbox here for a minute, There are many reasons why I decided to write this package in R. One, R is growing in popularity amongst behavioral scientists. More and more scientists are adopting R. Two, it's free and open source, and this makes open science easier. Three, the R community is great. There's so much support, and folks are willing to help each other out. And last but not least, the data visualization is amazing. ggplot is a godsend, and it helps take our pupillometry results and, turns them into something beautiful. Now you might be asking yourself, what does GAZE-R add that other pupillometry packages don't have? First, I think that GAZE-R gives you a standardized and reproducible pipeline for pre-processing. Everything that you do in GAZE-R can be easily shared, and everything is transparent within the code. GAZE-R offers flexibility in choosing which pre-processing methods or steps you want to use and the parameters that are used. If you don't want to use a particular default in GAZE-R, you have the option to change that to meet your needs. I believe that GAZE-R is an easy to understand pipeline. I created GAZE-R as something that I would have wanted as a grad student, and I've tried to make things as easy to understand as possible. And this is one of the reasons why I wrote the GAZE-R paper that's in Behavioral Research Methods right now, is to provide kind of a detailed walkthrough of how to, pre-process everything. So inexperienced users of ours inexperienced R users could use it, as well as more advanced R users. One of the coolest things that I think GAZE-R has that other packages don't is that it's encapsulated in a container or a capsule. And CodeOcean is very similar to a Docker image where everything is encapsulated, and theoretically it will work forever. So there's no more worrying about OS or packaging compatibilities. GAZE-R should work forever, or as long as CodeOcean is free and open to folks. And what I'd like to do now is show you how to access the CodeOcean capsule if you're interested in that. To access the CodeOcean container, what you're going to need to do is go to the GitHub, so our GAZE-R GitHub, and then you're going to want to scroll down, and you want to click on the Open in CodeOcean button right here. And that's going to take you to the CodeOcean container. You will need to sign up for an account, and as a free member, you get 10 hours of computational time and 20 gigabytes of data, which I think is plenty to analyze your pupil data. And once you have duplicated this capsule, you can actually add your own data in here, and you can run RStudio in a cloud workstation, and you can use all of the GAZE-R functions to analyze your pupil data. And at the end of the session, when you close out, all of your data will be saved, and then you can export that to Python or MATLAB, whatever platform you prefer. So let's get back to the talk. To pre-process your pupil data, you will need to carry out a number of steps. You will need to read in your data. Typically, you have data from multiple subjects that you need to combine. You will need to deblink your data, and this includes extending the blinks. You will need to interpolate and smooth your data. Pupil data can be very messy. You will need to baseline correct your data. You'll need to reject artifacts, and this includes rejecting too much missing data, unlikely pupil values, and also very rapid changes in the speed of the pupil from sample to sample. You will want to align your time series to a particular message. and then you will want to downsample your pupil data. Lots of eye trackers sample at high frequencies, and you just don't need that to analyze pupil data. What I'd like to do is walk you through each of these steps and show you how you can implement that in GAZAR with ease. So let's get started. In order for you to install GAZAR, you will need to do it from GitHub. And you can easily do that by calling the install GitHub function from the remotes package. Once you've installed GAZAR, you can call the GAZAR package using the library function. Just as a note, you can use the RStudio IDE, and it's highly recommended that you do so. But if you're old school and you want to use the console, you can do that as well. More power to you. The data that we will be looking at today comes from 4 participants that participated in a lexical decision task that I collected probably 4 or 5 years ago. And in this lexical decision task, I presented individuals with type print stimuli and also cursive stimuli. Cursive words are non-segmented and ambiguous, so a letter in one context won't look the same in another context. So they're very hard to process. So I felt that this was an easy comparison for demonstration purposes. The data was collected with an SR iLink 1000 Plus. GAZAR can read in data from the SR data viewer. So you can export data viewer files. Those are usually XLS files. GAZAR can read in EDF files. And coming soon, GAZAR will be able to read in TOBE files. To read in SR data viewer files, what you'll need to do is you'll need to set the working directory. And this is bad programming form. You should never set absolute paths. I should have used the here package for this, but I did not. Once you've set the working directory, what you'll need to do is you will need to save all of the data viewer files to an object called file list. Once you've done this, you can use the merge GAZAR files function, which requires the file list, the name of your blink column, and the name of your pupil column. And you will also need to list file type. Here it is SR because you're using the SR data viewer files. You can also read in EDF files, but it's a little bit more complex and it's more involved. To read in the EDF files, you will need to have a path to your EDF files. You will also need to have a path for where you want your EDF files stored once they're converted. And similarly to the data viewer files, you will need to save all of your files to an object. Here it's file list EDF. And then you're going to want to call the parse EDF function, which is actually going to parse your EDF files and save them into a directory. Once you've done this, you're actually going to need to take all of those CSV files that you've just converted, and then you'll need to save them to this file list pupil samp object, and then you'll have to call the merge GAZAR files again, which includes the object that has all your CSV files, and then type here is EDF because you're using EDF files. And once you've done this, you will have a data frame or a tibble with all of your data with columns tidied up for you. To read in the data quickly, you can use data that's already stored in GAZAR, the pupil sample files _edf.xls. And then you can just read that in, and you will have a tibble that has a subject column, a trial column, a time column. And what's great about this is that it's already converted to milliseconds for you. It's not eye tracker time. There's a pupil column, X, Y coordinates column, a blink column, a message column, and then you also have behavioral data. And GAZAR can also parse your behavioral data as well, but I'm not going to go into that for this talk because I don't have enough time. I want to point out that GAZAR can work with data from any tracker as long as you have these columns: a subject column, a trial column, a blink column, a pupil size column, a time column, and a message column. If you have all of these columns, you can use GAZAR. It's going to require some data wrangling on your part, but you can use GAZAR if you have these columns. Again, I'm working on some functions that will make this a little easier, but that is going to take a little while. So look for that in future iterations of GAZAR. Once you've read in the data, you're going to de-blink the data. And blinks are major artifacts in pupillometry research, and most eye trackers treat blinks as missing data. Now, you can just treat blinks as missing data and not do anything else. But what's suggested is that you actually extend those blinks before and after. So as your eyes are closing and as your eyes are opening, those values are spurious, and you should probably extend them. And GAZAR does this for you. Using the extend blinks function, we can extend those blinks forward and backward in time. So you need, you're going to need your pupil column name, and then you're going to have to say what the duration you want to extend forward and backward. Here we're doing 100 milliseconds, but you can do whatever you want. You're also going to need the sampling rate of your eye tracker. Here it's 250 hertz. And then once you have run this code, what you'll get is a data frame with the column extend pupil, which will be your extended blink data. After you've done this, you will want to smooth or filter your data and interpolate, or you'll want to interpolate and smooth your data. Some researchers will just throw out all the blink data and not interpolate, but I suggest you do not do that. Instead, you should interpolate and smooth the data. In GAZAR, you can do linear interpolation, or you can do cubic interpolation. Sebastian Matteau has a different type of interpolation that I might include in future iterations of GAZAR, but I haven't looked into it yet. There are two types of smoothing algorithms that we can use in GAZAR. There's an N moving average or a Hanning filter. And again, in future iterations of GAZAR, we might include more smoothing functionality. What I've done in GAZAR is I've combined the interpolation and the smoothing function based on a recommendation from a reviewer. So you can choose to do interpolation first, or you can do smoothing filtering first. And interestingly, the choice seems to matter, so you need to keep that in mind when you're using this. So we can see that. So on this top figure here, we have filtering first and then interpolation, linear, and then interpolation, filtering second, linear. And we see that there's really no difference between the two. So it doesn't matter if you filter first or if you interpolate first when you're doing linear interpolation. Where it seems to matter a little bit is if you're doing cubic interpolation and you decide to interpolate first and then filter or smooth your data. There seems to be some kind of bias there, some overshooting, which is kind of interesting. So just keep that in mind when you're pre-processing your data. To smooth and interpolate your data, as I said before, it's all in one function now. You can use the smooth underscore interpolate pupil function. And to use that, you need to have the data frame or the tibble that you're using, and then the pupil column name, what you called your extend pupil column, whether you extended the blinks or not. So if you did, you have to list that as true. And if you want to do interpolation first or filtering first, max gap is just how many NAs you want to interpolate over. Type is if you want to do linear or cubic interpolation. Hertz is the sampling rate of your eye tracker, and N is just how many samples you want to average over. After this, you're going to want to baseline correct your data. In GAZAR, you can do subtractive baseline or divisive baseline. And in GAZAR, we use a grand average baseline based on recommendations from Sebastian Matteau's paper. In his paper, he showed that if you do a divisive baseline correction on a trial-by-trial basis, it can introduce some bias in terms of the proportion change. So he suggested that you just take a grand average of the baseline through all the trials and then calculate the proportion change that way. So that's what we've implemented here. And there's kind of two different functions that you can use to baseline correct. There's a baseline correction pupil function that just uses a numeric baseline. So this baseline window from 500 to 1,000. And this is if your timing parameters don't really change and they're kind of static. So you can call that. Another function that we have is a baseline correction pupil message function, which allows you to baseline correct based on some type of message. So you need the pupil column name, so the interpolated pupil column, baseline duration. So here it's just set at 100. You probably want to do 500 or 1,000, but Matlin showed that the baseline duration doesn't really matter too much. The event is the message that you want to baseline correct from. So here we have target. So baseline duration is set to 100, so that means that it will calculate the baseline duration 100 milliseconds prior to the target being presented or the message being displayed. Baseline method is the type of baseline correction you want to do. So here it's sub, which is subtractive, but you can change that to divisive if you'd like. So if we call this variable baseline pupil, we will get a data frame that will have a column for subject, trial, baseline, and this is going to be our baseline corrected pupil size in arbitrary units, time, pupil, etc., etc. So after we've baseline correct, we want to do some artifact rejection. So we want to throw out, missing data. We want to throw out, participants in trials that have lots of missing data. And it's recommended that you should remove trials and subjects with more than 20 to 30% of data. And you can do that with the count missing pupil function. What you'll need is the data frame or tibble, and then the name of the pupil column, and then the missing thresh function. And this is set at 0.2, but you can change it to whatever you'd like. And what I think is really neat about this is that in the console, it prints out how many trials were excluded and also if participants were taken out. And this would be important for papers that you write. You will also want to throw out spurious values or unlikely pupil values. And Sebastian Matteau recommended that you should avoid using heuristics such as 1 or 2 standard deviations above or below the mean. Instead, you should visualize your data. Sebastian Matteau did this within the context of baseline pupil sizes, but I think that this can be extended to the whole pupil time course. And you can easily do this by looking at a histogram of your data. And if you look at a histogram of your data, you might decide that you want to remove some of the tails. So here, anything less than 2,500 or greater than 4,000, we exclude from the analysis. You might also want to do a second pass of your data to look for large changes in pupil size between successive trials or samples. Dilation speed outliers are samples that feature a disproportionately large absolute pupil size change relative to their adjacent samples. In this equation right here, the absolute change between samples is divided by the temporal separation of the samples, producing the normalized dilation speed between samples. In this equation, let di be this pupil size series with corresponding timestamps, ti. The dilation speed at each sample, this d prime I, is calculated as the maximum absolute normalized change relative to either the preceding or the succeeding sample. Once you've calculated the speed pupil, what you need to calculate is the MAD, the median absolute deviation. And that's simply just the median of the entire sample minus this d prime I variable. Then you need to calculate the threshold, which is just the median of the sample, plus n, which is a constant. The larger n is, the more extreme values that are needed to trigger the cleaning process, times MAD, this median absolute deviation variable. And that's kind of encapsulated right here in the speed pupil function and also the calc MAD function. Next, you'll want to align your time series to some type of event or message. And you can do that with the onSent pupil function. What you're going to need is the time column, the message column, and the event that you want to align to, which in this case is target. And we can see that this has been successful. Time 0 is 0, and our message is at target. So this is how you would align your time series. Next, you'll want to downsample your data. As I said before, most eye trackers sample at very high rates, and you don't need that for pupil data. So you can use the downsample gaze function, and you'll need the baseline pupil onset or the data frame of all of your pupil data, the bin length, so this is the size of your bins, which here is 100 milliseconds, your time variable, and then also the variables that you want to aggregate on. So here it's subject, script, and time bins. And then this produces a nice data frame with subject, script, time bins, and then also our baseline pupil size within those time bins. And once you've done that, you're ready to visualize your data. And this is what the data looks like with our 4 subjects. And we can see that at the end of the time series, we see that the cursive stimuli are larger than the type print. Unfortunately, we can't make any statistical inferences, just based on eyeballing the data. Instead, we're going to need to perform some type of statistical analyses. And Drew is going to be talking about generalized additive models and growth curve models and the differences between them. So I'm not going to go into great detail on that, but I will say that Gazar has a helper function to perform growth curve analysis. Using this code poly function here, what it'll do is if you specify your polynomial order, so 3 in this case, so a cubic, what it'll do is it'll append your polynomials to your data so you can perform growth curve analysis. And if you set this draw poly function to true, it'll output this nice graph here. I would like to end this talk by discussing the future of Gazar. One thing that I would like to do is submit Gazar to CRAN. But before I do that, I want the community to be able to test out the package and work out some of the kinks. Once I'm comfortable with the state of Gazar at that time, then I'll submit to CRAN. I would love to have more support for eye trackers. So GazePoint and SMI, I would love to be able to support those eye trackers. I don't have those eye trackers, so if the community wants to help contribute, they're more than welcome to help me out. I would love to have a GUI or Shiny application for some of the pre-processing steps so we can visualize these things and make it easier for folks. I would also like to have better error and warning messages so it's more intuitive for users. And now I ask the question to everyone in attendance, what do folks want to see in Gazar? We can talk after this, we can talk offline, but I really want to know what the community wants in a pre-processing package. And with that, thanks for listening to my talk.